So it is time to actually start building the SKYNET fixture. And so we're going to start off, I want to show you the model real quick here on Fusion 360. And so basically what we're going to build today are these angle plates and then some of the other plates that go underneath it. And so one of the very clever things about this design is actually the fact that these angle plates for the head tube and the seat tube, they're both the same thing, which makes it much simpler for us. And so if I hide the welding table here, and we can zoom in just a little bit, so you can see it's basically just a plate with all these holes that we have to drill. And really, in my opinion, this is probably the most complicated part of the machining. Well, maybe not necessarily complicated, but just time consuming because there's so many holes. And then again, we're also going to make these right here that go underneath it. And on the back of it, we're going to drill the holes that mount these slides. Now for these, I'm going to talk more about those later as we make them, what their purpose is and all that good stuff, because there's some more clever stuff going on there. But let's go ahead and jump over to the drawings first, where it might be a little bit more clear what we're doing. So this should give you a better idea of what we're making here, and I'll point out some of the important things to look out for while we make the angle plates. I also want to say, once this project is completed and we make any revisions that we need, this drawing package will be available to anyone who wants them, so stay tuned for that. But I would say one of the most critical dimensions here will be these bore holes for the cosine bar system. It's a 9-inch length and it's set back 8 degrees. This one needs to be as good as we can get it, because any error that we make here will be added into every bike that we make with this system. And also note these holes that are used to mount those Delrin slides that I just showed you. We're using a small 1032 fastener to actually fasten them, but then 2 spring pins to locate it. So the holes for the spring pins are another that we need to make sure we can get as close as possible. The other holes are just counterbored or tapped. And of course they have a reasonable tolerance to work with. And this arc of holes is likely the trickiest part of the whole thing. And I'm including some useful info on the drawings for using the digital readouts PCD function. And I'll show how that works here in a bit as I'm doing it. I will say though, if your DRO does not have this function, maybe it's an old one or whatever, you could certainly get away with laying out these holes manually. You'll just have to really take your time and get it as close as possible. Because if they're not super precise, it's not going to affect the function of them. There is some wiggle room with how these work along with these slots. And for these, the beam support and the clamp blocks, it's also fairly straightforward. The slot width and length is not, super critical. We just need to allow room for our 1/4-20 fastener to move as we set the angle. And I think that pretty much covers the highlights for now. So let's go ahead and head out into the shop over to the mill and let's start making them. So now out here in the shop, one of the first problems we run into is this 8-inch plate does not fit inside a 6-inch Kurt vise. So I did it the easy way, and well, I just took the jaw off real quick and just used the vise body itself to mount to. Quick and dirty, and it works in this case just fine. So I'll put it up on some parallels and then get it clamped down nice and tight. And one of the first things we have to take care of, if you see there, the edge of this plate, straight from the guy I got it from, is sheared, or is it shorn in this case? I don't know. But we need to get that cleaned up so we can make it look nice and pretty. So I just put a basic, 3/4-inch end mill in there, went ahead and dialed it in and faced it off just a bit. So you can see here I'm just kind of finding the edge, touching off basically. And then I come back just a bit, dial in, I don't know exactly how much, maybe 20-30 thousandths, and then just went ahead and took the whole side off. And we'll go into fast forward here. And then once that was faced off, I was able to go ahead and zero out my DRO for that side, and then travel the 10 1/4 inches we need, plus the diameter of the end mill, face the other side, and then I know this plate is exactly 10 1/4 long. And then all that's left is to put in an edge finder and pick up the other edge so I'll know where I'm at on the plate. And here I'm just making sure there wasn't any big burr or anything like that on the edge for using the edge finder. So we come in, grab the edge right there, right when it kicks. And then it's just a matter of basically just putting all the holes in the right place. So I knew where the edge of the plate was, so I came into where I want the pivot to be, which I ended up considering the origin in this case. And then I moved over to the other side and made that one. And yeah, it's just a matter of, getting all the holes in the right spot. And I will say it really helps, make good use of the digital readout, because basically all digital readouts will have an absolute and incremental function. So essentially you can switch between as many, coordinate systems as you want while still maintaining your, we'll call it absolute zero at the origin. And so here we're going to go ahead and talk about the PCD function of the digital readout. So I'm going to pause for just a second, and basically if your digital readout looks like mine, like the numbers are the same, then that means it is the same regardless of brand. Because all of these that you can find for cheap online, they're made in the same factory somewhere in China or whatever, and they just throw a different brand name on there. But basically you just push that button for the PCD function, then we put in all of our information. So it starts off by asking you basically what coordinate system you're going to use. In this case we want the X and the Y axis. And then the center position is another one, and basically that is just, the center position is another one, and basically that's asking where we want the center to be. So in this case, that pivot was our origin, so 0, 0. And then it's asking us for the diameter, which is already in there. It's 11.156. I'm not sure I typed it in again or not. Yeah, I did. And then the next thing it's going to ask us is the start angle. And it's a little weird the way these work, but basically if your digital readout is different or this doesn't work, just read the manual. I mean, yes, they're translated horribly and hard to read, but it's in the manual. So the start angle in this case was, there we go, 98.370. And then the ending angle was 197.74. And then it asked us the number of holes, which 15 in this case. And then just like that, it spits out each hole for us. So basically it gives us 1 through 15 that we can use the arrow keys to go up and down to. And then all we have to do is make the X and Y axis go to 0 for each hole. So you'll see here I dial in the first hole. Basically we just zero both out and then we're in the right position. And after we drill that hole, we hit the up arrow or the down arrow to go to the next hole and then do the same thing again. And so here we can see, I'll just fast forward through all this, but as I go through each hole, you'll see it create that nice arc that we need. Now I put in 15 holes, but we do end up skipping one of them because that's the hole where one of the counterbore holes is, and that's on the drawings, you'll notice. So I came back through, drilled them all with the number 7 drill in preparation to tap them with quarter 20. And this is also the part I get everything that I know about machining. And I actually tapped them first and then came back through and countersunk them, which is no big deal because I used a tap follower to get the tap started. But it's supposed to do a little countersink, chamfer the hole before you tap it. It's just better that way. But for doing this, it's real simple. We basically just set a stop on the quill so they all look the same and dial that into where we want it, and then again we just go through each hole using the same the same function on the DRO. While we got it pulled up on there, we just stick with it and do each hole, and then they all come out looking really nice and even, and it looks like we actually know what we're doing. So there you go there, nice little pretty shot of all the holes. And so for the next step here, again, it's basically just making all the holes need to go. So here I'm drilling I already forgot exactly what size this was, but this is the size drill that I needed for the counterbore that I have. Basically just matches the pilot size. And so we just go through each one and put them where they need to be. And then next up, I went ahead and counterbored these. And so I'll show you how I set that up. I did a really quick and dirty way of doing it, where when we go up to the quill of the machine, we set our stop basically just using the fastener itself. Like, I set the counterboard down on the plate, and I used the fastener itself to set my gap there on the travel. And of course I started it in the wrong direction. Had to put it in low speed. But then we go ahead and we try it out. So we go ahead and do one hole here. You know, bore it down all the way until we hit the stop. Pull it out, and then we check it with the fastener. And in this case it worked out good, because I mean, all we're looking for, this is not a critical dimension in this case, all we're looking for is to make sure the head of the fastener is slightly below the surface. You know, too much obviously is bad, but you know, too little and it sticks out. So here we go, close up. But yeah, just put it in there, try it out, and yep, fits good. And so then here was drilling, you know, drilling out some of the other holes. That was for the 1032 fasteners that we use. And I want to show you this part. Check out this tap. If you've never seen one of these before, these are awesome. These are actually designed, if you notice that cut on the tip, it's designed to push the chip out of the bottom of the hole. So in this case, for a through hole, it's perfect. And so once you get it started, you can just crank it on in there. You know, the way your grandpa showed you, where you go forward a half turn then back a quarter, whatever, you don't have to worry about that. And these are good, you know, nice sharp taps, so you can feel it. It just sails right through. But you just screw it all the way in and all the way back out, and that's it. And you can power these, but I don't have a tapping head or anything like that, so I just crank it in by hand. Now, I want to show you this next shot here is really cool. This is the bottom side of one of those holes as I tap it. And check out that chip as it comes out. So yeah, just screwing it in like by hand, just like in the first shot, and that chip just comes all the way out in one long form, just like that. I thought that was pretty fun to watch from this angle. And there it is. So I'm actually jumping around a bit, because this is the order that I did it. Basically, I went ahead, I didn't have an end mill that I needed. I was waiting for it to be delivered. So I went ahead and jumped over to the other plates that we have to make, the beam support and then the clamp block. So I faced them to length, because the length was not a very critical dimension. I just got it as close as we needed. You know, centered up on it with an edge finder again, and then we just poke the holes where they need to be. Now I'm skipping ahead again. These are the slots that we need to create. And here's the way, I did it the quick and dirty way. I'll show you here, but basically I just took a drill bit that was slightly smaller than the size that we need and drilled out the center of each end of the slot. And I've got that marked out on the drawings. But basically just drilled them out, got most of the material out of the way. Then I took a nice dull scrap bend find 2-flute end mill of the right size, in this case 1/2 inch. And then we just plunge it down in there. Then we get it all the way through, we lock the quill in place, and then we just slowly travel over. Now again, this is the quick and dirty way. If you want a precise slot, this is definitely not the right way to do it. They did come out just fine though, and especially for our case, this is perfectly acceptable. But yeah, if you want a super precise width on your slot, this is definitely not the best way of going about it. But I'll show you a close-up here in just a second. It came out fine. And there you go. You see the finish on the inside of that. You know, it's going to be perfect for what we're doing. Now there was one side, you can see one of the problems here. That right there, I believe, is from the end mill just recutting some of the chips. But I just took a file to it and they came right off, no problem. And now one more thing, for the beam support blocks, they actually need to be, this is 1.5 inch bar stock aluminum, but it needs to be slightly less than 1.5 inches. the purpose for that is so when it's supporting the rail that's actually holding the head tube, it needs to be slightly thinner than the extrusion. That way, because this is not a precise fit with the fasteners we're using, it does not interfere with the cosine bar setup. So in other words, if you just put your cosine bar or the 1, 2, 3 block and gauge blocks on there, it's not going to interfere if it's, you know, messed up slightly. So we cut it down to, I think it's spec'd at 140 thousandths on the drawings. So I just faced one side, flipped it, and took the equal amount on the other side. Then came over to the belt sander here and basically just making it look pretty. So I went ahead and just kind of knocked these corners off, rounded them a little bit, make them nicer. And I mean, nothing too complicated there. I just did that to all 4 corners on both plates. Now here's this is a smoke 'em if you got 'em sort of thing, but I've got this burnishing tool from some work I've done in the past, and it makes really quick work of making these plates pretty. I mean, it's dirty and messy, so I got the door open, but you know, you'll see how fast it is. It's basically just a Scotch-Brite wheel, and you can see right there, it just hitches them up. I mean, it takes 30 seconds. So now jumping back, I had the end mill that I needed for this boring operation. Ideally, you would have done this while you still had it in the vise. So what I had to do, you know, in the interest of just getting these parts done, is I came back and did it last. But, you know, I just got an indicator in there and just indicating back in on the hole so I know exactly where it needs to be. And, you know, nothing too complicated there. I think you can see a little bit. See, we're getting closer. But I got it dialed in, and then we did this milling operation, or boring operation. And this was a technique that PVD also told me about, but basically we're going to use the power feed to bore it. So first thing is I set up my stop on the quill nice and solid all the way down, then lock it. And then we're using the knee here and a piece of paper to basically feel the surface. And you can see right about there, and you can kind of hear it. When the paper grabs, we know we're almost there. In fact, the paper is about 5.5 thousandths. It's pretty thick paper. So now when we bring the knee up another 5 thousandths, the edge of our end mill is exactly at the top of the plate. So I went ahead and bring it up 5, and then I dialed in the depth that we need, which in this case was, I believe, 313 thousandths. So you'll see here, it's just 3 rotations, then plus another 13. And so then the whole idea of this is that we're going to center back up over the hole. I'm going to hit the power feed on the mill, and it's going to go down exactly 313 thousandths, you know, give or take, and then stop automatically. And we'll see, it worked out awesome. So check this out. I start it up, pull the power feed, and then it just runs down in there, nice and quick and easy, and here it goes. And so once it hits the stop, we go ahead and stop the machine, hit the brake, and then we pull it up out of there. And look at that finish too. It turned out awesome. So you can see there, beautiful finish, nice sharp end mill. And then this part's for the haters. I don't have a depth micrometer. I need to get one, but I used the calipers. So, you know, but again, we're just going for close enough here. This is not a super critical dimension. But check that out. I was shooting for 313 thousandths on the print, and yeah, I'd say that's definitely good enough. And that pretty much covers it for these plates. Again, we're going to talk a lot more about some of this stuff as we go along, but this is the basics of the angle plates and how I made them, and you know, some of the stuff to look out for. So let me know what you think, and next week we'll keep on trucking with a lot of these parts. So thanks for watching, and stay tuned for the rest of this series. Well, I had to have one little mistake in there, didn't I?